All right, hello everyone. Welcome back to Advanced Plus Plus. This week we're going to be talking about fair machine learning. So this week we're going to keep this a very accessible workshop, very beginner-friendly workshop for everyone. So please, if you just clicked on this video on the recording or something and you're worried, don't be worried if you're not super familiar with a lot of the mathematical justifications behind machine learning models, or even like the advanced structure behind deep learning or anything. Don't worry about it. We're just here to kind of discuss a lot of topics to make people more aware of the current situation in regards to bias in machine learning and how this relates to just bias in general amongst humans in society. So yeah, thank you everyone for coming out. As always, the slides to the workshop are right here. You can see them at the bottom of my screen right now. So please open that if you want. And yeah, let's get started. So once again, here's the slides. I'll just put them on a separate slide just so it's more clear. And then if you guys want your attendance points on the ACM website, it's lavender this week. So, and you kind of have to be here in person to get those, since I think it's only open 6 to 8. So if anyone in person wants that, it's lavender. And here's the schedule. So yeah, first workshop we did transformers, then we did adversarial examples. These are all posted on the ACM UCLA ACM YouTube channel. So feel free to check those out. Those are a little more, they expect a little more prior knowledge, especially the transformers one. The adversarial examples one, I think, is pretty accessible if you have a basic foundation in machine learning. But this week we're all set for anyone who wants to join us. So that's awesome. And then we have 3 workshops after this one. So we're going to be going over autoencoders next week, optimization, regularization, and a really cool quantum machine learning workshop taught by some other ACM AI officers for our last workshop. So hoping y'all will come out to those. Okay, awesome. So let's dive straight into it. So before we start talking about fair machine learning, I want to give a very, very quick kind of like 2-slide high-level intuition behind supervised machine learning, just so anyone who's like not familiar at all, like, will have at least enough information to like understand like where a lot of these problems are coming from and why they're such a big issue and the scale of the problems that we're actually dealing with here. So yeah, I want to start off with a quote from Kane Miller. So, oh, actually, before I get started, I want to thank, I don't know if Arjun's here right now, but I want to thank Arjun. He's an ACM AI director, and he put on a fair machine workshop as an internal workshop for us. And we're kind of giving this again to the public now because we thought it was a great workshop. So a lot of these slides were originally developed by him. So I just want to thank Arjun before we go forward. So yeah, so let's look into this quote. It's going to give us like an intuition for what's going on. So we need to understand that all software we write, even barring machine learning, all software we write is like intertwined by human influence, right? Humans are intimately involved with the software that exists because humans are the ones writing it and dealing with it, right? So like it says, algorithms are written and maintained by people, especially machine learning algorithms adjust what they do based on people's behaviors. And we'll see why this is the case, because fundamentally, especially in deep learning, a big problem we'll see is that these models are extremely data hungry. And the data that we give to the models is a product of data sampled from human beings that are not necessarily perfect random samples of what we see in the real world. So as a result, a lot of human prejudices that we may have, and that I'm sure most of us are very familiar with, are going to manifest themselves in machine learning models. And we'll explore, and the point of this workshop is partially to explore why these propagate through machine learning models and are a problem in machine learning. And an even larger part of this workshop is just to become aware of these problems' existence and things we can do to be aware of them. So I want to stop here and just open it to a discussion to like any examples of things people have seen just in the media, like any news you've heard of, like examples of like software or specifically machine learning like exhibiting bias. If you guys have like seen any of that, there's many examples just like in like social media and whatnot. So if you guys can think of anything, feel free to speak up.
Saw this instance in the news once where an Asian person, there's basically some like facial recognition software where they thought his eyes were closed because he was Asian and just had like smaller eyes than I guess some other people. So that was one instance that I've heard of.
Yeah, that's a great example. Actually, I remember last quarter, one of the classes I took, the professor actually gave that exact example to talk about this exact problem. So that's a great example. We also, I'll stop for a second if anyone has anything else to add.
I think this was like a pretty long time ago, but I heard of one where there was like an AI that was being used for hiring, and they would look at the resumes, and if the person was a woman, there would be a lower chance that they would get hired, and then they tried to correct for this by not giving the machine the gender of the person, and instead the algorithm just looked for like women's activities or like women in coding club and stuff like that, and it would basically judge based on that.
Yeah, that's a fantastic example. We're gonna a lot of the examples we're gonna give just because it's convenient and easy to think about. A lot of the examples we're gonna give are probably in the context of like job hiring and stuff because that's a place where it's very important to make sure we're doing unbiased screenings and whatnot. So I believe when Arjun taught this workshop, so an example he gave regarding this was exactly what you said. So Amazon, I believe, used to like have a machine learning algorithm that would do initial screenings to kind of filter out resumes, and then yeah, like you said, they actually it was actually gender bias. So they ended up doing a few things, like you said, to try to circumvent the problem, but ultimately it was unsuccessful because of the reasons you pointed out. Like it would just look for features that may be indicative that someone identifies as female, and it still had the same problem. So they actually ended up, I think, scrapping it completely. So great example, yeah. Here's another example. So Justin, did you want to say something?
Yeah, so another just point to kind of frame the perspective of this workshop is while we are kind of detailing different things that we can do to make sure that models are fair or as fair as they can be, there are also things that we have to consider like, is this an ethical use case? Like, even if we do have a perfectly fair model, like, should we even be considering this use case of machine learning? And also like acknowledge like different power asymmetries and societal things that may influence our models as well.
Yeah, that's another important point to think about is that there's a lot of these problems are that we're going to discuss are as you'd expect very very difficult to tackle in terms of solving them flat out. So a really important thing that we need to do is once we're aware of these problems, we need to just be aware of like, is it really necessary to like use a machine learning model to do this task? And like something that a common like problem, or you can call it a problem, but a common circumstance that we found ourselves in 2021 is that machine learning models are very very commonly used to conduct like tasks like that are in some way involved with humans, right? Like this doesn't necessarily have to be the case. So for example, machine learning has been used in many applications to do things good for the environment. Like it can make predictions about rainfall, it can make identifications of certain tree species, things that aren't necessarily related to humans. There's a lot of applications for machine learning here, but unfortunately, like we see an overwhelming use of machine learning, uh, prone to possible biases because we're just doing things like facial recognition, using it for job hiring, things that are places that we need to be very careful and conscious of bias. So if we're just going to look at this example, there was an paper published, I think the name of the paper was Pulse, and it does I think it was a generative adversarial network. Don't worry about what that is, but the idea is that it upscales basically low resolution images, right? So I'm sure most of us on the left here can recognize that the image on the left is supposed to be a picture of Obama, right? It's a very low resolution image, but as humans, most of us living in the United States, probably, um, like most of us know this is Obama, right? But like we see like the model, um, said this was like some white dude, right? So obviously this isn't right. And like that's a big problem, right? So fortunately the paper published like an ethical consideration section where they stated they were very aware of a lot of these problems, and they were important. They were sure to like point these out, so that's very good. But nonetheless, like this is a problem that emerges, right? And we're gonna explore like why this is the case throughout this workshop. Okay, so just so I'm sure we all are familiar with like how prevalent at least AI is like throughout like the society that we live in, especially like it's all over social media. It fuels so much of what happens on the internet in terms of ad personalization, especially in terms of what we see and what content is viewed on the internet by a certain individual is heavily influenced by machine learning algorithms in the present. So it's really important to understand that no matter where we go, at some level, something is likely being fueled by some deep learning machine learning model. And I'm sure we're all familiar with it, with how prevalent this is, but we're going to see that this causes like a lot of nasty problems when it comes to biases and feedback loops that kind of just spiral us down into creating more and more bias and kind of polluting the data that we use to train things. And it's kind of a really big problem. So yeah. Now, these two slides are not about fair machine learning. They're just giving you guys a very high level kind of intuitive idea behind what deep learning and machine learning is about, just so we understand kind of at a high level why a lot of these problems might occur. So yeah, let's discuss high level machine learning, right? So modern machine learning models, so particularly deep learning models, are very, very data hungry. They have many, sometimes millions, billions of of learnable parameters that need to be tuned. And the way these parameters are tuned is you kind of, in the supervised case, the idea is you feed the model data. So you can think of the model just as an input-output function. You feed it a bunch of inputs, it gives you an output, and then you know what the output is supposed to be. That's part of the data. So based on how well your model aligns with what the data is supposed to be, you're going to change this function, this f of x here. If this is our model, you're going to change it, you're going to update it and play around with all of the parameters inside of it until it basically can identify things accurately. So basically you want to keep doing this until when you pass your input into your output and then you compare the output that the model gives with what the output is actually supposed to be, you want that to be correct as many times as possible. Now, I'm not going to detail the optimization behind how this is done. What's important for you guys to understand is just that what this function ends up being is extremely heavily influenced by the data that's given to the model. Okay, so it's going to learn solely from the data that's given to it. That's the only information that you're really feeding into it that dictates what this model actually ends up being. Okay, so the only goal that we usually in the traditional sense look at is we have a certain task and we want to maximize the accuracy that the model has on the task. So in this example, let's say you're trying to identify whether something's a cat or a dog, right? It's just a binary task. So there's only two options, right? You want to maximize when you input, you want to maximize the problem, like the cases in which when you input an image of a cat, it'll tell you it's a cat. And you want to maximize the amount of times when you input a dog, it's a dog, right? It very intuitive. But this only looks at one metric, and that's the accuracy of, am I getting this right or wrong? And we'll see in this very simple case of whether it's a cat or a dog, there's not many implications or things we need to think about in terms of bias. But we'll see in the real world, often just looking at the accuracy is going to be very problematic. Because if the model's only concerned about maximizing the accuracy of some very specific, often very simple task, then it's going to not really be cognizant about biases that it's instituting. Okay. So this is just another slide to give you guys another high level overview, right? So this is like, you can think of this function as our template function, right? It's some model, right? It's some machine learning model, some function. And the thing we pass into it is these X's, right? So these X's can just be like an image of a cat, right? And initially what this model is really going to be doing is influenced by these two parameters, these two theta parameters. These are often called learnable parameters or weights of our network. So the idea is you have some template function, right? It's just some function that has the form like theta 1 x1 plus theta 2 x2, right? But these values of theta can be absolutely anything, right? So there's like infinitely many functions that satisfy this structure because you can just change this value of theta. And the whole point is we want to use the input to keep changing this value of theta until we find these values of theta that are going to perform the task we want correctly. So in the previous slide, we were saying we wanted it to identify whether a picture of a cat is a cat or a dog, right? So in this case, we want to keep passing a bunch of data into this model, a bunch of these x's over and over again, until we can tune our parameters enough, these theta 1 and theta 2 values, such that the accuracy of the model will be good. Okay. Is there any questions about that? Really, the only thing you guys need to understand about this is that what this model ends up being is just very influenced by the data that's fed into it. So I'll pause for questions here since I just rambled for a while. Okay, cool. Also, feel free to like use the chat at any point. We have Justin and Varun who are monitoring the chat for you guys, and I'll be monitoring it while Justin's talking. So yeah. Okay, now let's actually get into the fair ML part. So there's kind of common or a few common ideas that I'm sure we've all maybe thought about as we've been growing up and we've watched like technology and computers develop. So kind of before machine learning was very popular, we kind of viewed computers like and robots in general as just like very mechanical, like, okay, you are giving me the right answer to this problem. And that's because in the past, a lot of the problems that we've asked computers to solve are very deterministic, right? So for example, back in the 1980s, even earlier than that, the only things we were really asking computers to do were very deterministic computations, like 1 + 1 is 2, 3 + 3 is 6, blah, blah, blah. Things that have just a definitively correct answer, right? And then this has led to a kind of phenomenon in most of our brains of thinking that what the computer says is the truth, because we've commonly asked computers in the past to just tell us the output to some very deterministic task, right? So we've fallen into this kind of mindset that what the computer says is the truth. Unfortunately, in recent years, we've had to like adjust this mentality significantly, since a lot of the tasks we're now asking computers to solve are very non-deterministic, very complex tasks, not like 1 + 1 is 2. You can be asking a very high stakes task, like, does this person deserve a job? That's a very difficult question to answer. And there are many, many attributes and variables that need to be considered if we're going to make a correct decision in that regard. And the correct decision is not necessarily an objective decision. Even as a human, if you're going to sit there and determine, is this person qualified for a job? It is not necessarily an objective answer. There are many factors, and it's all based on, oh, does this employer value this attribute more, this attribute less? Are there biases that this employer is unconsciously using when they're making their decision? These are all things that even as a human making that decision are problems, okay? And they're just as much of a problem for a computer as they are for a human, okay? So you guys might have the question like, well, a lot of these tasks that we're solving, they're inherently based on discriminating between things, right? So in the case of whether someone's like deserving of getting a job or not, this is a discriminatory task in that you have to discriminate between individuals who you believe do deserve to get the job and individuals who you don't believe deserve to get the job. So that's inherent to the problem you're asking, to the question you're asking. The fact that you're performing some sort of quote unquote discriminatory task in and of itself is not a problem. The problem is what criteria you are using to make this discriminatory decision, right? And this is a problem like we're all very familiar with as humans. When we need to make decisions about things that are not necessarily objective, we need to make sure we're not biased off of certain attributes. So for example, if you're choosing a job, you need to make sure you're not biased based on someone's gender, someone's race, someone's sexual orientation. These are all things we're familiar with, and these are problems that machine learning models need to address. So the problem isn't so much as, oh, well, machine learning is inherently discriminatory, so we can't do anything about it. That's not the problem. The problem is we need to look at what criteria are okay for the machine learning model to make the discriminations based off of, and which criteria are not okay. And it's often very difficult to determine when a machine learning model is using criteria that we would consider not okay or discriminatory. So for example, it's very hard for us as humans, when we look at a machine learning model, for example, if a machine learning model is trying to discriminate whether someone deserves to get a job or not, and then we're just observing, like they input like the profile of some individual and then it outputs yes or no, right? When we're making these observations, it's very hard for us to determine, oh, did the computer make this decision because this individual is a female? If this individual was a male, would the computer have made a different decision? It's very hard for us to make these to answer these questions, because a lot of times the machine learning model is viewed as a black box, right? In that you just input something, it does some magic inside of it, and we don't know exactly what it's doing, and then it gives some output. Now, as a machine learning researcher, you'll have some intuition behind what it's doing, but it's very hard to pinpoint exactly what features it's using. And that's a big problem. Okay, so let's have some more general discussions about what makes a criterion justified or unjustified. And then I'll kind of go over some definitions, and then we'll kind of hopefully stop to have a discussion about some of these things, and we can discuss some examples. So there's the first question, which is that of practical versus moral irrelevance. Okay. Now, sometimes there are certain criteria that in a certain context are like relevant to the task at hand. So I'll give you guys an example. Let's say you're trying to determine whether or not you can hire someone. I keep going back to this example, right? Hopefully you guys can maybe chime in with some more creative examples, but I'll keep going back to this example as a basic one. So if you're determining whether you want to hire someone, maybe a question that you need to ask, and I'm sure if you guys have applied to internships or whatnot, you've been asked this question of, will you require are you an international student? Do you require company sponsorship or something? So this is a question that the company needs to ask, right? It's a question that they need to ask because, well, if you require company sponsorship, that may impact whether or not they're willing to hire you, because they may not have the resources to provide a company sponsorship to you as an individual at that time. So there's a specific reason why the company's asking, oh, are you an international student? They're not just asking because they want to be racist or whatever. There's a reason they ask you that. Now, let's look at another example where there would be a criteria that a company might ask you that isn't relevant, right? So let's say you're applying to some office position, right? And let's say you're a disabled person, you are in a wheelchair, right? You have to be in a wheelchair, right? And then you go to the job interview, right? And it's an office position, right? You're just sitting at an office, you're at a computer all day. You're mostly sitting. So in this situation, it would not really, your ability to perform well on that job is not influenced in any capacity by the fact that you're in a wheelchair. So it would not be a justified criteria for the employer to not hire you just because you're in a wheelchair. Now, if we want to look at the flip side of that, so let's say you're applying for a job that's like you're working in like cargo, like you have to move like a bunch of boxes around, right? Like let's say you're working at an airport, you have to you're the person who like puts all the luggage into the plane, right? So that requires you need to be able to walk around. You to do the job, you need to be able to walk around. You need to be able to grab this suitcase. You need to be able to put it in the plane. There's certain things you need to be able to do with a certain level of proficiency that a certain disability may prevent you from being able to do so. And in that case, then the employer could have the right to be like, okay, look, we need someone who can do this with a certain level of proficiency. Unfortunately, because your current situation is not permitting you to do that. That would be justified in that specific case because it has an impact on your ability to perform in the job. Whereas if you're in an office, it doesn't really matter, right? So you need to look at the domain of the problem that you're trying to assess and then determine what criteria are justified and what criteria are unjustified. This is a very high level idea that everyone needs to always be cognizant of, right? So does anyone want to give some additional examples? I want to open it to discussion of maybe give an example of one criteria that would be a justifiable criteria to make a decision based off of in one case, but not justifiable in another case. And this will kind of relate to the next point. Any ideas?
I have kind of an idea.
Okay.
So for example, sometimes, especially for women, they're asked like during the job interview if they're planning on having kids anytime soon, which is like totally inappropriate to ask. In 99% of the cases, I think, and I'm like struggling to come up with a case where it would be okay, but like I don't know, maybe
Maybe you're a wine taster. I don't know.
yeah, like a bartender, or not a bartender because you can't drink on the job, but yeah, something where you're like drinking alcohol and it's for your safety
Right.
and the baby's safety or whatever.
Yeah, I think that, yeah, that's a good example. Yeah, definitely, like, that's a great example, because in almost every situation that's not an appropriate question. But like, yeah, like you can maybe look at some very specific context, like someone who's applying to be a wine taster or something, then like obviously you wouldn't want that. That would be maybe a more appropriate question to ask for your own safety and for the safety of your child. So that's one example. And this goes into the next point of the criteria, whether or not a criteria is justified is based on the domain that we're looking at. So I've already given an example of this. Maya just gave an example of this. I'll give one more example. So I think Arjun's here now. Hi Arjun. But I remember the example Arjun gave was, for example, if you are applying for example, the position of like the president of some LGBT plus group, right? It might be justified to have a discussion of your sexual orientation, your background in that field, because maybe the people who you would be representing feel like they would want someone who has similar experiences to them and someone who can relate to them. So in that case, maybe it would be a proper discussion to talk about their person's background in terms of sexual orientation. But once again, if you're applying to a job, it's completely irrelevant. It would be it's not an appropriate question to ask, and it shouldn't be considered in the process because it has no impact on your ability to perform on the job. So I think we've spent a while on this, so I don't want to drag this on too much. So let's go to the next slide here. So yeah, so you'll notice a lot of these things aren't necessarily exclusive to problems to machine learning, right? These are a lot of problems that are inherent to human nature, and a lot of these are propagated in machine learning models, and we'll explore that in the coming slides. So let's talk about the difference between disparate treatment and disparate impact. So the kind of high level simple way to think about this is that in disparate treatment, you're being overtly biased in some way. You're intentionally being biased. So an example of this would be if you are hiring applicants, you would give a certain test to test. You'd give a certain test of proficiency only to a certain group of people. So let's say if you are of Asian American descent, you have to pass this this examination about American history or something. But if you are white, then you don't have to take this exam as part of the job application process. That is overtly racist, right? You are intentionally giving someone disparate treatment between two different groups of people in order to assess whether they're capable of doing the same task. So this is obviously overtly racist. Now, let's look at another example of things that are just more like inherent or not intentionally caused, but things that might arise just as a result of the institutional practices, institutionalized biases that exist, right? So for example, you could do something like giving everyone a test. So let's say you're still doing the job filtering thing. You give everyone a test, this American history test, right? And that's like a very big factor in whether or not they get the job. Well, you would say that this would be biased towards people who are maybe born and raised in America, went through the American education system. Now, a question of whether this is okay or not has to do with what you're actually trying to assess for the task, right? So if the job description is American history teacher, sure, test people on American history. But if the job is like software engineer, this doesn't make sense, right? Even though you're giving everyone the same task, some people are going to perform better at that task as a result of their background, even though that task has no bearing on their ability to do the job. So this would be an unintentional or informal like way of being like unfair, even though you're like giving the same task to everyone. Okay. Does anyone else have maybe two examples, maybe one of something that's overtly like bias and something that's more arise as a result of this of the situation or background of individuals? I will wait.
I heard interesting just today situation that happened back in the 70s with hiring police officers, and so they had like particular physical requirements, but like one of the requirements was basically like you had to be at least like 5 foot like 11, 5'10", and that kind of basically served to filter out most women applicants. And you know, it's not necessarily being particularly tall doesn't necessarily make you better at this particular law enforcement job. And so I was thinking about that when we were talking about those.
I think this is that's a great example of this. And a lot of times this can still be something that's like more overt, even though you're giving the same task to people, right? It could still be something that's intentional. Just because you're giving the same task to someone doesn't mean you're doing it unintentionally, right? So someone, this could like because it's kind of like an excuse of being like, no, I'm not being biased because I'm giving everyone the same task, right? Like for example, in your case, the case that you just brought up about you having to be 5'11" or something, right? Like you are probably aware that the average height of women in the United States statistically is lower than the average height of men, right? So when you make a decision like that as an employer, you are in a way, it is possible that you are intentionally imposing this metric that's, although it's imposed the same across everyone, it's a metric that's possibly intentionally opposed in order to like disallow certain people from getting entrance into the position. So it can still be intentional even if you're giving everyone the same sort of like ground here. So this raises, like, if going off of this raises deeper into the question of equality of opportunity versus outcome. So this kind of is just the classic question of equality versus equity. And I'm sure like maybe most of you have maybe discussed this in some capacity in the past. So let's have a quick discussion about this. Okay. So, actually, yeah, let's stay on this slide. So this just comes down to the question of like, you may be like instituting a system for everyone that's quote unquote equal, but it's not equitable. And equity is important because it accounts for the different backgrounds that people are coming from, right? So you need to be instituting a system that gives everyone the same like chance or ability based on certain criteria that you are testing for that are appropriately measured in order to get a certain job. So for example, something that would be technically quote unquote equality, but not equity, is giving everyone an American English test in order to get a SWE job. Technically, it's equal because you're giving everyone the same job, giving everyone the same task, but it's not equitable because it doesn't take into account that different people from different backgrounds may not be able to perform proficiently on this task. And that's not okay because in the case of you hiring for a SWE job, it doesn't matter if you can solve an American history test. So this is something we need to be cognizant of. Okay. So now we've kind of like passed the general discussion, and we're going to talk about how these problems kind of manifest themselves in machine learning models at a high level, and how some of these problems happen. And a lot of these are based on like basic statistics that very intuitive statistics that I'm sure most of us can get behind here. Okay, so this is something we discussed previously, right? So the previous mentality was back in the past when the job of computers were oh so simple of solving, arithmetic tasks and very deterministic objective tasks. Computers would do great for us, right? And they had this was for much of the history of computing. This is what computers were tasked with doing. So this has led to an unfortunate reality that many people trust computers too much to make decisions for things that are not necessarily objective, right? So this has led to a phenomenon in the recent boom of machine learning that we've seen in the past decade, that people just very kind of in an unrefined manner just ran in and just, like I said at the beginning, All they cared about was increasing the accuracy of one task as much as possible without accounting for certain biases that may result as a product of only putting the constraint of increasing the accuracy as much as possible. Okay, so now in recent years, we are realizing this is a problem. We're realizing that if we only kind of constrain a model to increase the accuracy of something as much as possible, it's going to give it a lot of freedom to like to institute a lot of bias into the way it classifies things. And this isn't just a result of the criterion that we're using. This is, like I said, a result of where the data is coming from, how the data is sourced. And these are all things we're going to look at. And this is where Justin, I think, is going to take over. So I'm going to stop my sharing, and Justin's going to talk about these 5 points with you guys of things that can kind of cause machine learning models to be biased. So I'm going to stop my share now. You can go ahead and share, Justin. I think I might have to enable it. No, you're co-host, so it should be fine.
Yeah, I think it's going through. Okay. Let me know if that's showing up for everybody.
Yeah, you're good.
Awesome. Okay. So I just want to take a quick interlude to plug another ACM AI event that we have going on. So this coming weekend, we're going to be having a game social night. So just as like a little break from midterm studying, I'm putting the event link in chat. So we hope that you can come. We're going to be playing different games like chess, code names. Just look for details on that event page, but we hope that you can make it out to that. Awesome. So Paymon left off by giving us a great introduction into the different issues that we need to be aware of when considering bias within machine learning systems. So I want to direct your attention to this sort of model on the bottom right. So this is kind of a high level structure of what our machine learning model is going to be structured as. So,
sorry,
and this is kind of applicable.
Sorry to interrupt. Do you want to press present or?
Oh, sorry.
Yeah.
Thanks, Varun. Awesome. Is it showing for everybody?
Yeah.
Cool. So this representation is true of any data-driven model. So what we're trying to do is we're trying to take the state of the world, which is very rich in content, and we want to reduce this into a measurable, quantifiable thing in the form of data. So right there, we can kind of see where potential biases can be introduced. And after that step, we push this data into a model through a process which we call learning. So this is another vulnerable area for bias to be introduced to our model. And after that, we employ the predictions of our model to perform actions on individuals, create like game plans or direct companies, which impact individuals. And they in turn give feedback to our model. And this will actually shape the landscape of our world as we see it. And you can see that this is kind of a cyclic structure. So in bias that can potentially be propagated through our model, it can only get worse if we continue to let it go unchecked. So the types of issues that we're going to be looking at are skewed sample, tainted examples, limited features, sample size disparity, and proxies. So before we get into that, are there any questions on this kind of high level overview? Great, so we'll jump right in. So first, skewed sample. So let's assume that we have a situation in which we are employing a machine learning model for some sort of predictive policing task, a very noble cause. So we can assume that we have initially a high level of reporting in crime in one area of a particular city, let's say like Los Angeles. So in this particular case, we can see that the initial state is somewhat subject to bias. So based on historical data, we can see that like policemen may have been patrolling this area more heavily, and as a result, have resulted in more arrests in that area. So we'll see a initially high level of reporting in crime. We take this data that we've generated from years and years of policing, and we try and push this into a model. Unsurprisingly, our model will predict a high probability of crime within this particular area of the city. And as we saw before, we take that model to perform action and direct our police program. So we'll send more police resources, like more troops, more cops to that area in order to have some sort of policing in that area. So we can see that this increase of resources into this area, as well as the subconscious kind of nudge from the model, will induce officers to make more arrests and report more crime in that particular area. So future observations of this crime will confirm the predictions of this model. And since we're funneling all of our resources toward this area, we'll find less outliers for our model to balance itself out on. So we can see that from a historical bias, using the model and impacting the way we conduct business as a police force will only cause that initial bias, which may have been small, to compound. And this is kind of known as a self-fulfilling feedback loop. So we can see that there's not really a good way to get out of this cycle, which is definitely a big problem. So can we, first of all, are there any questions on this particular concept? Great, everyone's a fast learner. So if that's the case, then can I get an example maybe of a different use case in which we might see skewed sampling that maybe leads to some sort of feedback loop?
There could be some machine learning model that says, or that looks at several cities and says which one is the best to move to based on some metrics. It predicts one is the best. If it's popular enough, people will move there. There's more data and more positive reviews. If it weighted those, that city would continue to be desirable to move to. The algorithm would continue to say it is desirable to move to, and that would be a self-fulfilling feedback loop.
Definitely, yeah. Great example. So there's also another example that, another plug, I'm sorry, but ACMW is holding like audiobook read-alongs of weapons of mass destruction. And they kind of pinpoint on an example where, if you guys are familiar with like the college university rankings by US News, that can be kind of an example of like skewed sampling, particularly within a feedback loop where people will want to get into this like top school, and that'll like push it to be a top school. So we see this kind of cyclic nature of this algorithmic ranking system. Great. So we'll move on to our next issue, which is tainted examples. So this kind of arises when we think about an ML model as a whole. So models are only as good as the data that you feed it. So if we have a actor which is already biased and we want to train an ML model based on that actor, or based on this data collected by like this biased person, we're only going to perpetuate bias throughout our model. So an example of this can be maybe a biased recruiter doesn't favor students coming from Howard, which is a HBCU, and Wellesley grads, which is a liberal arts college for girls. So if we were to take this data as is from the recruiter of which students would be a good fit for our company and push that into our model, we'll see very obviously that our model is using this bias to leverage a particular objective for the model. So we'll see this model is actually also biased. So you can think of this model as a sort of stochastic parrot in which it samples a distribution, the stochastic part, and then it acts as a parrot. So it kind of mimics what it hears. So we have to be really particular in the way that we generate our data and make sure that it's not tainted.
Yeah, so like to add to that, so the idea is kind of like to extend on the college example that we have on the slides. So like the idea would be like you generate like this big data set of people, a bunch of individuals from a bunch of different schools, and then if the certain recruiter that initially did the recruiting, like because we're doing supervised machine learning, we're basing our models off of some data that's been collected. So if in the data that's collected, a very low percentage of individuals from Howard and Wellesley were ended up getting a job for this specific position, then when we train a model that, for example, tries to predict, okay, are individuals like from certain individuals like qualified for this job or not? If the data indicates that a lot of people from these areas or these colleges were not fit to get the job, then the model is going to say the same thing. So if the model sees if you input a person from Howard into the model, it's going to more likely say that this individual is not qualified for the job because the data would commonly say that. So because the data was biased, now the model's biased. It's that, yeah. I was just reiterating that.
Awesome. Thanks for the clarification, Paymon. Are there any lingering questions on tainted examples? Great. So moving on, we have limited features. So this is the case in which our training data might be different for different population groups. So features may be less informative or less reliably collected for certain segments of our population. And this is particularly heinous when we have a large majority group versus different minority groups. So an example of this can be if we are a geospatial company and we're trying to collect data for like earthquake monitoring. And let's say in a affluent area, we have the funds, our office there has the funds to purchase like more precise equipment. And when we take our readings, we have readings that don't really have gaps in the time steps that we take readings. Let's also say that they're accurate to the 5th decimal point. Whereas if we look at an area which is a little less affluent, we have maybe older instruments for measurement that can have like faulty breaks within the system in which we lose portions of data. And these are also a little less precise. They only go to like the 3rd decimal point. So in that case, we can see that the features that we collect in the affluent area versus the less affluent area, they're going to be different in their quality. So features collected in the less affluent area might be less informative or less reliably collected based on the situation. And then accurate predictions for our majority group might not be the same as accurate predictions for our minority group. They won't be, they won't coexist. A way to get this point across is if we look at a model with a certain reported accuracy, let's say 90%, that doesn't mean that it's going to have a 90% accuracy for each person group. So let's say we are, again, predicting like the likelihood of an earthquake within particular areas. And let's consider that we have 2 groups, the affluent city and then the less affluent city. It's not the case that they're both going to be 90% accurate, that we can predict whether an earthquake is going to happen or not. But we can be like very, very accurate on the affluent group and be less accurate for the less affluent group. And on aggregate, if we report our accuracy in a particular way, we can come across as having 90% accuracy as a whole for the model. And in this example, we can kind of see the disparity and bias within our model in that it doesn't serve all people groups. So are there any questions on this particular concept? Or Paymon, if you have something to add as well.
I was just gonna say, there's a lot of examples, I think, of this. So it doesn't even have to be that the features are like less reliably collected. It could even be that the features are like completely absent, right? So can for like some minority group. So then it's just not representative, even to the capacity that it should be for a certain group. So can anyone think of any examples where basically like the data that you're representing is not going to be representative of the population you're saying it's representative? So someone says in the chat, can't unmute, but college admissions for students from international high schools versus domestic high schools. Yeah, that's a good example, right? Because there's going to be a lot less applicants from international high schools. So the data that you can collect regarding the maybe proficiency and abilities of people from international applicants for college admissions is going to be not as high quality, right? Because we all learned in statistics, basically the more data you have, right, you can regarding a certain group, the more accurate your kind of aggregate mean of that data is going to be in representing what you're trying to represent. So if we have a lot less data, then our data is going to be more noisy. It's not going to be as accurate, and we're not going to be able to make as good predictions about things. So that's a good example. Yeah. One example I'll kind of throw in there is, I think Justin gave this when we were preparing. He said, like when you're doing kind of polling on the internet, maybe like for a certain, Justin, do you remember what you were talking about with the internet? I forgot. It was something about how more affluent people have access to
Yeah,
the
so for a lot of machine learning applications, a lot of the data is collected via the internet. So it might be in the case of like people-oriented applications that we have more data and more reliable data, more informed data on people that use the internet more, which is more likely to be affluent people that have stable access to the internet, whereas people that maybe don't have constant access to the internet might not be as well represented in terms of like the data that we have might be a little spotty. An important distinction to make, which we'll get into on the next issue, is there's like a nuance, but do we have any particular questions on this before we move on? Awesome, okay. So next we have samples, sorry about that. We have sample size disparity. So let's assume for the case of argument that we have a world in which all of our features are collected perfectly. So this is in stark contrast with our limited features problem, in which the data that we actually collected was of lesser quality. So in this case, for all people groups, we're having the same features and they're equally informative, equally reliable. Even so, with a large sample size, which is required for these really data hungry models, if we have a majority group, we might observe that our ML model will improve its training error by solely focusing on this majority group and casting aside like the minority group and kind of taking the hit and willingly having poor performance on this minority group, because for the most part, it does well on the group that is the majority in its training set. So this is like a very nuanced difference from limited features, in which like all of our features are perfect, but we can see that like with a improper distribution of groups, we can still see bias perpetuate in the system, even with perfect data.
Yeah, so I can maybe give an example of that. So if you're trying to, let's go back to the job selection thing. You're trying to make a model of, to predict whether people are qualified for a job. Let's say, I'm just gonna make up numbers that I know are wrong. So like, I'm not saying these are correct numbers because they're not. Let's say, the the true distribution of people who are trying to apply for this job and who want to get it is 90% white and 10% black. That's probably not going to be true, but let's just say it is for the sake of argument. Now, if your model is being trained on this data set that is perfectly sampled from the fact that 90% will be white and 10% will be black, well, your model is going to, because remember, the job of the model, as I mentioned at the beginning, only cares about maximizing the accuracy as much as possible. It doesn't care like if it gets a certain group wrong, as long as it can get, it finds some path that maximizes the total accuracy as much as possible. So let's say if 90% are white, 10% are black, it's going to spend a lot of time making sure it can get those 90% right, because it knows that most of the time it's going to get data from that 90%. So if it can get the 90% right almost all the time, then when it gets data from that 10% group, if it gets it wrong sometimes, it's not concerned about that as much, because it's not going to be seeing data from that group as much. So then you'll run into a situation where perhaps it can correctly do the classification on the 90% group, maybe 95% of the time it gets it right. And then on the 10% group, we were saying of the black individuals, on the 10% group, it only classifies it right like 60% of the time. But on net, right, I can't do the math in my head right now, but on net, you're still getting like, I think over 90% accuracy there on your combined total data set. So, and think of it from the perspective of the model, right? If the model instead just focused on the minority group, let's say it got 100% accuracy on the minority group of 10%, right? And then it gets 50% accuracy on the majority group of 90%. Then its accuracy is going to be like very low, right? It's going to be like 53-ish, 54-ish%, right? It's going to be very low. So that it would if it's only concerned about increasing the total accuracy, it would much rather focus on that majority group. So the kind of nuance that Justin was talking about here is that even if we do a perfect job of sampling things, the model's still gonna not care. It's still gonna be biased. So you can see how this compounds, because in the real world, we're never gonna have a perfectly collected feature set. And on top of that, so we're probably doing a worse job of collecting the minority features in the first place. And then even when we collect the minority features, the problem gets worse just because of the model isn't going to care about the minority group as much. So you can see how there's multiple levels of this problem in a compound. Yeah.
And Paymon, Arjun, our like resident Faramel expert, he dropped a great example. If you want to make that more concrete, just by looking at this case study.
Well, I have to read it, so maybe you can go ahead and then we'll.
Okay, so why don't we come back to that example if there are other questions, but for the time being, we'll move on to our next issue, which is proxies. So this is kind of the case in which you have a machine learning model and you knowingly have a sensitive attribute that you don't want to have factor into your prediction. So we as designers will kind of withhold this data, this particular feature from our model and say, here, go do what you want with everything else. But we're going to be unbiased because we withhold this sensitive feature, be it like gender or race or religion or sexual orientation. This isn't a guarantee because within our data set, we might have features that are really strongly correlated with particular class membership. So for example, we can have a case in like a hiring algorithm. We don't want to have gender factor into our hiring system. So we purposefully take that out and we withhold it from our model. But let's say we also have the user's internet browsing history. I know not the most realistic example, but let's say we have it. It's a weird company.
Are you sure it's not realistic?
It is probably realistic. So we do have your internet browsing history. And let's say we see that in your history, you watch a lot of ACM AI workshops, like a lot, like on repeat, which is really weird. But you also buy like dresses or makeup. So these are things that are more stereotypically correlated with woman gendership. So by this way of this feature, you can effectively have a conduit that is very highly correlated with your gender without introducing gender into your model at all. So this is kind of a cut and dry example, but within these machine learning models, they're going to be super, super deep with not very interpretable results and mechanisms behind them. So it's hard to determine, like we can see that internet search history might be a very obvious proxy for gender, but it might not be the case. Like let's say your hobbies are included in that, and somehow that can be shifted its way toward your gender. So it's hard to say like which feature is too correlated with a sensitive feature. Are there any questions on this final issue?
Yeah, basically the idea is even if you take out the direct kind of attribute that, like the big idea is even if you take out the attribute that you're trying to not discriminate based off of, like you just take it away from the model, the model will on its own kind of find its way to that attribute indirectly through other kind of information that you give it. And then it can still be biased as a result. Because the kind of high level idea when you're doing these classification tasks is that the model basically takes a bunch of low level features and then it keeps trying to upscale it, or not upscale, kind of compress it into more and more high level information rich features until you can finally make a classification. So, and there's many, many layers usually in these deep learning models, so that the model has a lot of time to kind of craft its own features. And then what it might happen that the model indirectly, even if you take out gender, for example, the model might indirectly kind of craft its way into figuring out, okay, this person is a female somewhere in the process of its prediction. So yeah.
Awesome. So just to do a brief overview, we have 3 different problems that we have to be cognizant of. So if we are discovering unobserved differences in performance, in our model performance, meaning that we don't really see, if we break it down, if we break our like testing data into groups, like we evaluate group by group, we don't see a particular difference, we might be having an issue of skewed sampling or tainted examples in which our labels are a little bit messed up. So like our reporting, or like our reporting is kind of messed up. So we have to be wary of that. Another issue is coping with observed differences in performance. So this is between different groups. So say for men and women, there's like an observed difference. That might be a case of limited features in which data is better reported or more thoroughly reported for men versus women, or there are more like women in our data set than men. So we'll see like a sample size disparity. Another one is kind of trying to see the causes of disparity within our predicted outcomes in terms of correlation with different features. So we might have to be aware of like proxies for sensitive attributes that we don't want to factor into our decision-making model. So based on these different issues with bias in models, we should be able to kind of identify and attribute different problems that we see within our performance to different problems within our data set, or how we are learning using this data.
Yeah, so the big idea here is we can use these kind of categorizations to maybe figure out the source of where bias is coming from. And that's a really important first step, is identifying where the source of the bias is, right? So like Justin showed in that kind of cycle that we had before we started talking about these 5 attributes, bias can be introduced at the data collection stage, in the training of the model itself, and so on and so forth. So there's many different areas in which it can be introduced, and it's important to kind of dissect these 5 different categories, none of which are necessarily mutually exclusive. It's probably very likely that multiple of these are happening at once, but it's very important to look at these and figure out, okay, there's something wrong with my data collection process. There's something wrong with the criterion I'm using to train my model. Like the way I'm training my model is bad and it's causing bias. So these are important things to be able to pick up and identify. Just like finding a bug in a computer program, right? You have to be able to first figure out where in the code your bug is, and then maybe you can tackle it, right? Same idea. Figure out the source of the problem, then you can tackle it from there. Which is tackling it is the harder problem. But yeah.
Awesome. So now we're going to get into the different criterion we can use to make sure and ensure that our model is not perpetuating bias and that we're acting fairly. So Paymon's going to lead us through a quick run through of these different criterion.
Yeah, don't be scared of the notation. Honestly, like we're gonna give like a very like not mathy explanation of it. So if you're interested in the more mathy explanation, then feel free to pay attention to that stuff, but it's not too important. Okay, Justin, do you want to hand over the share to me?
Sure.
Okay. Okay, are we all set?
Looks good.
Okay. Yeah, so just some basic notation, like suppose like X is our input. So like if we saw at the very beginning, X would just be like what you're feeding to the model. So like an image of a cat, for example. A is going to be our sensitive attribute. So yeah, e.g. like gender, right? So if we want to make sure we're not discriminating off of gender, we need to define this attribute gender, right? C is like think of it as the output of the model. So it's like what the model thinks the answer is. And then Y is the actual answer. Oops, sorry. Y is the actual answer. So it's like the ground truth. It's what the real answer is. C is what the model thinks the answer is. Y is what the real answer is. X is what we input to the model. And A is the sensitive attribute that we want to make sure we're not biased towards. Okay. So there's kind of 3 criteria that we use here. This one is pretty simple. Okay. It's independence, right? So we're going to use this this example that Arjun used for the for when we're talking about this. So the example is we're kind of doing we want to do ad placement. We want to selectively like give ads to people for a certain job position, okay, on the internet. So we want to determine, so what we need to do is the thing we're trying to determine is this person looking for a job, right? So if you're thinking about an algorithm that decides, should I post an ad for this job for this specific individual? The criterion that we need to think about is this person looking for a job? If the person's looking for a job, then you want to display the ad. If the person's not looking for a job, you don't want to display the ad, right? So that's what we need to, that's what our model's predicting. Does this person want a job right now, right? So there's a ground truth, right? Which is like the reality of, does this person want a job or not? Which is the value Y, which isn't on this slide, but it'll be on the next slide. Then there's the prediction, right? C. So this is, does the model think this person wants a job? And then there's A, the sensitive attribute. So let's unpack this. So this is saying, all this is saying in English is that whether the model decides or predicts that a person wants or is looking for a job should have no bearing on their gender. So given that you know their gender, the prediction of whether they want a job or not shouldn't change. So given this additional information of their gender, it shouldn't matter. So if you don't know their gender, the probability that they want a job should be the same as if you do know their gender. So hopefully that's pretty self-explanatory. There's not really much more to that. That's just a very kind of simple check you can do to see, okay, like, does this, like, is this it, or is the output of my model influenced by whether or not it knows the gender, right? If you give it the gender and then it changes its answer, that means the model is biased, right? Because if you give it some additional information that shouldn't change the decision and it does change the decision, that means it's biased. Okay. There's also the additional problem that comes with this of how do you test for all of these things, right? Because there's so many potential sensitive attributes that we might need to account for, right? So gender is just one of them. We can think of a lot of other examples: race, sexual orientation, birthplace, zip code. There's so many examples you can think of, right? None of which should have an impact, hopefully, on whether they predict you want a job or not, because those are not relevant to whether this individual wants a job or not. So this is the first example. So let's talk about some problems with this. There's a lot of words on this slide. Don't worry about it too much. Most of this we've already touched on in some way, but let's break it down. So Yeah. So the biggest, I'll just focus on one main thing on this slide, which is that machine learning is lazy. So this is what we've been talking about in the past, of how the machine learning model only cares about the accuracy that it's outputting, right? So it doesn't care about what trade-offs it has to make in order to reach that accuracy. So on this example, we say like a false negative prediction. So if it incorrectly says it's a negative, or if it incorrectly says a positive, these things can be traded out. If it sees that it can kind of like lose a little bit of accuracy by not caring about false negatives, and then instead allocating its kind of resources to making sure it doesn't have any false positives, and it sees that'll increase its accuracy more, then it's going to always do that, right? Because all it cares about is how high the accuracy is. So in that sense, we say like machine learning is lazy. And I think it's a kind of, in a way, it's kind of a refreshing statement, counterintuitively, because I like to think of it as, although this can cause a lot of problems in terms of bias, it does mean these machine learning models aren't as smart as we think they are. So if we're worried about ML models becoming sentient and taking over the world, don't be too worried, because they're really not as smart as we like to make them out to be a lot of the time. They're a lot smarter than we make them out to be in certain ways, and they're a lot dumber than we make them out to be in other ways. So, and this is one way that I would call ML models a little bit dumb. So yeah. Okay. So I don't want to spend too much time on this slide. So let's go to the next slide. Okay, here's another criterion, separation. So this one's a little bit harder to work our head around. So yeah, let's try to work our head around this one. So wait, I'm actually gonna look at my notes, because I wrote a really good way of thinking about this in our notes. Okay, so suppose someone's looking for a job, right? So suppose we know they're looking for a job. We shouldn't change the probability of giving them an ad based on whether they're a male or a female, right? So if we already know that they want an ad, the output of the model shouldn't change just because the person's a male or a female. Okay. Now this one is a little bit harder to wrap your head around, and I would say the next one is even harder to wrap your head around. But the big point here that you should take away from all three of these criterion is that they're all mutually exclusive, and it becomes more of a philosophical argument as a result. Is that the big thing you need to look at is that because of all these things are mutually exclusive, which means if you meet this criteria, you'll never meet this one. And if you have, or this one, right? You can't have all three of them at once. It's impossible, which seems kind of contradictory, right? Because, well, I'm setting out all these different criteria for, okay, I need to meet this, and this to say my model is fair, but it's impossible to meet all of them. So there's two frames of reference you can look at it from. You can say everything's fair because I can always meet one of these criteria, or you can say everything's unfair because I can never meet all of these criteria. So this becomes a question of, what are you judging fairness off of, and what does it make the most sense to judge fairness off of, right? So I remember Arjun, I don't remember the details of the example you gave, Arjun, but I remember you gave an example in which someone was some group was, I don't remember the context of the example, but some group was saying how your model's unfair, like you have bias because it's not meeting the independence criterion. And then the people who constructed the model said, well, no, this isn't actually a problem, we met the separation criterion, right? And then it becomes the question of like, okay, well, can you say anything? And like, why are these criteria the things that are the most important? These are all questions we have to ask ourselves, like what fundamentally makes a model fair? And can we really test for all sensitive attributes? Can we, because these are all things we as humans have to decide, right? It's a kind of a moral question of, because a computer has no idea what these sensitive attributes should be. The computer has no idea, oh, like I shouldn't factor gender in here. It doesn't have some moral compass. It doesn't know. We have to tell it, right? So if we tell it, you shouldn't care about gender. Okay, then you can like specifically test for this, right? We as humans go in to our model and we'll specifically like test for this or test for this. And that only tests for gender, right? Then we have to choose another criteria that we really don't want to be biased towards, right? Then we need to do these tests for those criteria. So it becomes a very difficult question, right? of how are we going to actually have fairness across everything. The question can be constrained to a small scope if we only look at one criteria like gender, but the question quickly becomes more complicated when we just look at fairness in general. Then we have to consider all possible criteria that our models shouldn't have any bias towards, right? So then it becomes very difficult. So yeah, I don't think it's too critical that you understand these in detail. So I'm not going to spend too much time on them. If you are interested in them, uh, message me, Justin, or Varun, or even Arjun after the workshop, and then we can have a cool discussion about it. But I don't want to spend too much time on this. But yeah, this is what I said, right? All of these are mutually exclusive, so you can never have all of them at the same time. And there's yeah. So like I was saying, I think Arjun has a proof for this, right, Arjun? I think it's like pretty short. So, but you should know that you can't have all these at once. So it causes a lot of problems. So yeah. Now let's quickly. We talked about a lot of. So let's overview like what we've done in this workshop so far. So first we talked about a lot of like inherent sources of biases and different types of biases and how we can judge whether something's biased or not. Then we talked about how human biases can often propagate through machine learning models and how this is kind of a self-fulfilling feedback loop that'll just make everything worse and worse and worse and it sucks, right? So let's talk about ways we can make it better, right? So what can we do, at least in the machine learning sense, to kind of mitigate these problems as much as possible? And unfortunately, we'll find that a lot of times it's very difficult to do this. And a lot of times this begs the question that we asked at the beginning of the workshop of, do we have to ask ourselves, do we really need to use machine learning here? So just think about that as I hand it back over to Justin as he talks about these last few slides for you guys. So these will be pretty quick. So we're almost done. So
very, very quick. Thanks everyone for hanging in there.
Yeah.
Sorry, give me a second to get the share started. Sorry, Paymon, if you have the slides open, do you mind sharing it?
Yeah, I'll share it. You can just tell me when to go to the next slide. Okay, there you go.
Thanks. Okay, so we're just going to do a really quick run through of the different ways we can ensure fairness algorithmically. So the first is pre-processing. So next slide. So this is dealing with your input data before it even touches the model. So again, we are using the same notation. We have our input features X, our sensitive feature A, and we want to kind of map this data into a different feature space. Don't worry about what that means, but we're just trying to distill this data and filter out the sensitive attribute. So if you look on the left side, we're trying to maximize I, which is information. So we're maximizing the information of X into Z, and we want to minimize the information about our sensitive attribute as we go to Z. And then after we get this kind of filtered out training data set, we're going to plug this data into our model. So this is in hopes that we're kind of taking away information about our sensitive attribute while preserving a lot of the richness of our original data.
Yeah, so one example of this that I guess you can think about. So it's literally not as complicated as it sounds. So one example of this is like how we were talking about at the beginning of the workshop. If you want to try to reduce the bias towards gender, well, just remove that information from the data, right? Try to get rid of that information. Now it can get a little more complex than that, since this can deal with kind of proxies at a certain level too, since there are it's not quite as simple as, okay, well, like we can just remove like the information about gender. It also takes into account certain things that may be linked to gender, right? So certain proxies, and then it tries to filter those proxies out as well. So not only are we removing the information itself, like, okay, this person is male or female or non-binary, etc. We're also removing any sort of information that may like let the model like kind of figure out on its own what the gender of this individual is, what the gender of this individual is. But what's hard about that is that a lot of times if you remove that information, you end up removing a lot of other information that might be information that's actually useful towards what your criteria is, right? So you might end up accidentally removing something useful. So it's a little balancing act of trying to like Justin said, I think that's a good word, distill your original data. So you filter out all those proxies and the data itself as much, the sensitive data itself as much as possible, while retaining as much of the rest of the information as possible. Yeah. So next slide, Justin.
Yeah, we can move on.
Right.
So another way that researchers will try and mitigate bias is by addressing it at training time. So we're going to minimize our loss function. So this is just some sort of mathematical formulation. We're trying to minimize our errors, basically. So we're improving our model performance, but we impose additional constraints on our model. So if these probabilities look familiar, they are. So we want our predicted outcome, C, to be independent of the sensitive attribute. So we want our probabilities to be within this range epsilon. So we want them to be as minimal as possible. That's kind of like the high level intuition for this sort of constraint.
Yeah, and we can kind of formalize this again with an example. So like if we're doing the if we're trying to determine whether or not someone's looking for a job, so if we want to show them the ad or not, right? So this is and our sensitive attribute is gender. Let's say 0 is male and 1 is female. So we can say that given that the probability that they're looking for a job, given that they're a male, should be roughly the same as the probability that they're looking for a job given that they're female, right? So it shouldn't matter whether they're a male or a female. And another higher level way of looking at this is a way to try to make our model a little smarter. So remember how a few slides ago we were saying how machine learning is lazy. Like we were saying, it's lazy because it only tries to maximize the accuracy, the total accuracy as much as possible. Now, us imposing this additional constraint like this, in a sense, is trying to make the model a little more cognizant of bias. It's trying to make it smarter, because we're going into the model and telling it like, look, you also have to pay attention to this. Like you can't be screwing up this. This is very important that you get this right as well as getting the accuracy right. So not only now the model has to worry about more than just the accuracy. It has to worry about also making sure these two probabilities are roughly the same. So it forces the model to be a little more aware. It's like, hey, model, look at this. You also need to not screw this up. So that's another way of thinking about it.
Thanks for that, Paymon.
Next slide.
Yeah, we can move on.
Okay.
So the last one is post-processing. So this is after the training of a model. It's going to consider like model performance. So there's something called the ROC curve, receiver operating curve, but it's not really relevant for us. Just know that it's a measure of how good our model performance is. So what we're going to try to do to mitigate bias is compare these two performances for different groups. So our model performance on these different groups. Again, using the same example, let's say we have a group for men and a group for women. We want to see our model performance on each group. And after plotting this curve, we want to graphically find like the intersection by which our model is best serving both groups. So this will kind of be like an overlaying, and then we'll find that point of model parameters. So like we'll tinker with our model a little bit so that it's most fair for maximizing its service to both men and women.
Yeah, basically, if one of these represents the curve for the males and one of them is representing them for the females, I think the idea is you want to maximize the overlapping area, right, Justin?
Right. Yeah. So that'll be for the ROC curve. Yeah, we're trying to get the max performance for each group.
Yeah. So then it's kind of going back and looking like, so once again, this is the same idea as this last one, but we're doing it a little differently. So in this last idea, we're kind of telling the model like, okay, look, you have to like also pay attention to this. And it forces the model to go pay attention to it. Now, in this situation, let's say you didn't force the model to pay attention to this, right? Now you have to go back in later and then see, okay, did the model pay attention or not? And if the model didn't pay attention, then you can go back and then play around with it a little bit. So this can be the example of maybe that your model has very high accuracy, right? So a lot of people in machine learning, they'll look at their model, they'll be like, oh my God, I hit 90% accuracy or whatever. I'm done. I don't care about this anymore. But good machine learning researchers will be cognizant of these biases, and then they'll go in and they'll do this post-processing analysis. They'll look at the outputs that their model's giving them, and then they'll do things like look at, oh, is the accuracy of is my accuracy of prediction on the minority group as good as it is on the majority group? If it's not, then I need to go back and change my model, even if my accuracy is good, right? Because we talked about just because our accuracy is good doesn't mean it's good on both the minority groups and the majority groups. It's likely only good on the majority groups a lot of the time. So yeah. And then this is the last slide. So we made it. These are some things we should be cognizant of and things we should be doing as machine learning researchers and just citizens of the world. So go ahead, Justin.
Yeah, so we threw a lot of information at you guys, but just if there is a sort of thing we want you to take away, it would be this slide. So again, recognize that ML is domain specific. So we want to understand the legal and social context of the application of these models. So like we said, different attributes are sensitive for different domains. We want to make sure that our model is acting serviceably toward all groups within a particular task. Next, we want to also scrutinize our data, not just the model. So a lot of research done right now within the machine learning community is based on establishing state-of-the-art and best performances for pre-existing models on pre-existing data sets by just minute changes to like a single parameter or something like that. But there isn't as much careful thought given to our data set and how it's generated. So we want to kind of break this paradigm and be critical of our data and how it's represented, how it perpetuates bias within our systems.
Yeah, to add to this point. So yeah, so you'll see a lot of current literature in the field. So they'll do what Justin said, is where you take some kind of base model that some kind of breakthrough paper introduced, and then they'll change a lot of little things to get the accuracy, like, oh my God, we improved it by like 2%. Amazing. And then a lot on the other side of things, there's a lot of papers that introduce things called benchmarking data sets, which kind of addresses this in a sense. And the idea is the paper will kind of introduce a big collection of data that the researchers have developed in some manner that can be used to kind of test machine learning models. And in recent years, there's been a greater push towards making sure these benchmarking data sets, when it applies to human examples, are very equitable. They're representing populations in a fair manner, and there's been more of a push towards this when creating new benchmarking data sets. And this is very nice because when we have more equitable benchmarking data sets, it'll start to sometimes expose poorly trained models or biased models. Because if we see that a model was originally trained on a bad data set, and then we use this new benchmarking data set that is maybe more equitable and it does a better job representing stuff, we'll see that the bad models typically, or the biased models will typically have worse accuracy on these more equitable data sets, because the model doesn't know how to deal with these minorities, the minority groups as much. So let's say when we originally trained the data set or trained the model, it only had to deal with let's say 5% Asian American population for whatever task it's trying to do. And then let's say it just kind of disregarded that 5% of the data set, and then it just focused on doing really well on the 95%. So then it got pretty good accuracy. Now you go back later, someone releases a benchmark data set that's maybe more equitable, and maybe it's more representative of the true proportion of the Asian American population. Let's just suppose that's 10%, right? Let's suppose it's probably not correct. I'm not even giving a specific point of reference. I'm just saying, let's just say it's 10%. Then if you go back and test the same model that was trained on the bad data, then it's going to do worse on this one, because now it's gonna get an Asian American example 10% of the time instead of 5% of the time. So now it's gonna screw those ones up twice as much because it has to deal with those 2 times as much as it would that it had to in training. So this can kind of, when we make better data sets, it exposes kind of, to an extent, it's not perfect, but it helps expose biased data that models that were trained in a more biased manner.
Awesome. So after that, we want to consider long-term effects and feedback loops and potential interventions rather than just observing like static one-shot problems. So one-shot meaning we want to have a model that is, it uses a small set of data and then it's ready for shipment. But we want to see how model outputs will influence future model outputs, whether that be in impacts to people that influence the state of the world, or data sets, things like that, that we have to be conscious of. Another thing that is particularly relevant now is we want to establish a qualitative understanding of when or why machine learning is the right tool for a particular application. So again, I'm sure you guys have seen a lot of different companies use AI or machine learning or data science as buzzwords, but we want to be really critical of like why we use these systems, when we use them, and what are appropriate use cases, so that we're not injecting unneeded bias into systems that would benefit greatly from not using ML, particularly within human-facing products. And lastly, we want to establish understanding of what constitutes negligence. So we might be tempted to become obsessed with not introducing any bias into machine learning or data or the world as a whole, and that might stifle a lot of innovation from up and coming companies or machine learning researchers that are just getting their foot in the door. We don't want to like choke them out and not allow them to grow and make mistakes and learn from them. But we do want to hold companies that are revered and well established and have that infrastructure to a higher standard of fairness within their machine learning applications.
Yeah, so if a startup with 3 people uses some deep learning model to do some prediction on their like little mobile app or something, and then we see it's like, oh my god, that it thought, like, for example, like this Asian American's eyes are closed when they're not or something. Maybe, of course, that's not good. We never like that. But we should get a lot more mad if something like that happens in Amazon's machine learning model or Microsoft's than some startup, right? Because we know we need to assess the resources available to all groups who are deploying their models and whatnot, and we need to be cognizant of that and not just maybe overly assign blame when it's not due, and we need to make sure we are assigning blame where it is due. So if Jeff Bezos is going out and deploying a bunch of biased machine learning models in his ad placement algorithms or what he recommends for you to buy on Amazon, we need to make sure Amazon's held accountable for this, and to a pretty high degree, because they definitely have the research funding and resources available to address these problems. But if we just let them go off and do these things, they only care about their profit. So you have to show them their profit is in danger if they're not addressing these things, because then they'll do something about it. That's an important thing to note. There's always a surrounding context behind things. So when you see some random news article that's posted on whatever knows news site saying like, oh my god, this machine learning model by this new startup screwed up with this one example, like, okay, like that's maybe more okay than if Amazon screws up everything, right? I feel like I'm thrashing Amazon a lot, but there's just in general, because I remember Arjun used that example. Okay, but yeah, and anything, I'll take it. We'll take a second to stop now in case you guys have any words of wisdom or things you guys want to add in terms of things we could be doing just as human beings to help this problem. Okay, that's fine. let's just make our closing remarks then. Once again, we want to thank Arjun for the slides. We basically just ripped off his slides. We added a few things, but yeah. We also highly encourage you guys to read this book if you are interested in this concept and you want to perhaps see a more mathematically rigorous explanation of how these problems are manifested, the things that people are doing in research right now to deal with these problems. A lot of the things we took from these slides are, or a lot of the things on these slides were taken from this book. So highly recommend it. And then there's a little kind of a more friendly tutorial here on Towards Data Science if you want kind of still like just to put your toes in the water. So that's all there for you guys as always. And once again, as always, please fill out the feedback form. We use your feedback to make the workshops better. And, you know, there's always room for improvement. So we'd appreciate as much feedback as possible. And I think that's it. Yeah. Thank you all for coming. We have a Discord, which you should join because it's cool. And you can ask questions on the Discord. We have like an AI section. You can ask questions in the AI sections. And then one of the ACM AI officers will answer you. And we like to have cool discussions. And we also have office hours. I think, Justin, is it Thursdays at 9 p.m.?
Thursdays, 9 p.m. Pacific Standard Time. Yeah.
Yeah, PST, sorry. Thursdays, 9 p.m. PST. And we have our Facebook group, which is where I think a lot of you get the link for this anyway. So most of you guys are probably already on that. But yeah, this is the last slide. So
awesome. So again, yeah, fill out the feedback form. Thank you guys for coming. It means a lot to see that you guys are interested in this topic. It's something that we've been wanting to implement within a machine learning workshop for a while. And to see interest in it is really awesome. Hopefully it gets integrated somehow within all of our tracks because it is a really important topic.
Yeah, this was our first time teaching this. So we hope to, like Justin said, integrate it more formally into our existing workshops content and maybe refine it based on your guys' feedback. So yeah.
Awesome.
I believe,
thanks everybody.
Yeah, thanks everybody. And I think Varun, you can end the recording now.